Thank you. So yeah, today I'm just going to give some broad strokes about how our ingestion pipeline works on Spark. So let me get started. So to frame the talk a little bit, our CEO spoke in this room at 11, talked about the business a little bit, but Ravel Law is a legal research and analytics company. So we signed a deal with Harvard last fall that allows us to scan all of the US's case law and present it to the public for free. We're very excited. We really think this information should be available to the public, and we're also excited to be able to have exclusive commercial rights to it to build analytics on top of it to sell it to our nation's largest law firms. So 2 products we have available for people today are Judge Analytics. If you have a legal matter in front of a judge, we want to give you the ability to see everything they've written in the matter which you're going to be before them, and some analytics on the citation patterns that they have on those matters. We also have a search product and a reading experience for case law. So what is case law? So I really like this quote from Justice Oliver Wendell Holmes. The life of the law has not been logic, it has been experience. So Congress will pass laws, those laws will be codified into statutes, and then a judge is the person who actually represents the law for a particular matter. So legislatures will pass things, and then a judge will see the actual facts of a matter and decide how those laws should actually be applied. So instead of it being sort of like this really pure philosophical thing, it is actually like our cultural experience that goes into how our laws get shaped. So in a more computer sciencey form, case law is a graph. The nodes of case law are legal opinions that judges write, and the edges are their citations. So right now in our corpus, we have about 7 million opinions. At the completion of the HLS project, which should take about 2 years, we should have about 11 million documents. Right now we have 54 million legal citations between those nodes. So just to give you a little bit of a couple screenshots of the product to give some context for what our Spark build pipeline needs to support. This is a screenshot of our search visualization. So as I said, there was case law is a graph, and when you search for a term, we try and show you the relevant citation network for the search results. So we'll segregate them by level, Supreme Court, federal court, and state court, and hopefully give you a more abstract overview of how this area of law has developed over time. Then we also have the Judge Analytics product. So if you follow any of the Apple Samsung litigation, that's at the district level, been in front of Judge Koh. Here we've selected the topic filter of patent, and you can see in opinions that Koh has written on patent law, these are the most frequently cited cases. You can also get some language on the particular cases that have been cited, and some pieces of text from the opinion she has written to get the sense of why does this judge lean on this particular case when they're explaining their reasoning. So in the judge's product as well, we have some different machine learning features to help people get a sense of what a case is without actually reading it. It's kind of funny, like this is all most legal writing is pretty readable prose, but the first thing I hear from attorneys is, if there's any way I cannot read a case, please make that happen for me. So we try to do that. So we have topic models. We'll try and say what a case's topic is. We have key phrases, things that we think are important and can help get to very specific, more specific search experience for the user. Motions, so we'll try and identify if a motion is being ruled on and what the outcome of that is. And then we'll try to get decision and summary sentences. So we use text strength to try to figure out what the matter of the case is, and then if we can identify in the opinion where a judge actually makes a decision, we'll try to deliver that piece of text to the user. Okay, so lots of stuff needs to go on in Spark to support this product. So we need to get our source documents from various data providers and get them into MongoDB in our opinion model. We need to extract the case law and statute citations and resolve them to the actual documents that they're citing. We need to do deduplication detection. We use techniques from the plagiarism detection space, but there's no universal identifier for case law. It's the publishing oligopoly sort of establishes where they appear in the books, but there's no universal way that people agree upon for saying this is this particular case. We extract the authors and try to resolve them to the actual judge entities in our database. We use LDA topics, and those support the text strength we do to try to get the case summary. Motion outcomes is one of our more complicated systems, several NER pieces in play. Then after that is done, we'll use some parsing techniques and then various classifiers to try to decide which part of the case is actually talking about a motion. Key phrase extractions, mostly NER, but several NER components in that pipeline. We do some semantic clustering of snippets from case citations that uses K and X means under the hood. And then finally, after all these steps are done, we need to export these things to MongoDB, Solar Cloud, and Cassavary. Cassavary is a little more obscure of the three. So it's an in-memory graph storage system, so we can store our entire citation network in memory and do some real-time analytics on the citation network for judge analytics and other things that we do. So I showed up at Ravel in late 2013. When I got here, we were on Apache Pig, and that was exporting to Cassandra. So 2014, I think around like the Spark 1.7, maybe 1.9 time, was doing a little bit of proof of concept work on Spark. And finally, around late 2014, we're actually switched over to Spark, exporting to MongoDB. No particular hate for Cassandra at Ravel Law, but we're very much dealing with documents, so a more document-focused store just really helped us out for our querying option, for querying and other things that we do. So why switch away from Pig? So here's some code. Like I could rant on this quite a bit, but you'll notice there's a lot of like type ceremony. So you're going to be getting things from various sources. We have very deeply nested data structures, so a lot of calls to flatten and then saying what fields of the things you're flattening. It very much has the feel of a sort of dynamic programming language where when you are exporting or dealing with the outside world, you are having to very verbosely explain the type information of the data you're dealing with. So Pig is mostly SQL, but you can make these things called user-defined functions. Once again, very much like a dynamic language, you need to describe the types of the things coming into and going out of the system. So that ends up becoming a very major maintenance burden over time. Also, even when you do have some type of information, you're frequently throwing it away into tuples. So yeah, if you've ever had to deal with JSON much in a typed language, you'll sort of know the pain I'm talking about. But Pig, it's very quick to get it set up and get started getting results. As soon as you have much of a code base, you can become very paralyzed by the amount of type ceremony you're sort of doing in your code. So got this quote from Robert Harper. I can thank him for ruining my Rails career with this argument. A dynamic language is a straitjacketed static language that affords less rather than more expressiveness. So in a typed language, you can have various types and no properties about them. In an untyped language, you have one type and you know nothing about any of them. So Google recently moved off of Sawzall. I really like this quote from that blog post. As a language grows, the rationale for using a domain-specific language rather than general purpose becomes more diluted. So being in Pig, having to really support the types versus being in a typed language like Scala, which has a lot of tools that are useful for us, it's a night and day experience. Yeah. So Spark makes you happier. So here's one of our steps in our build pipeline, very straightforward. We'll take an RDD of opinions, maps all of those to find a topic, and then below it is a function that is scoped directly to one opinion. So I can use the top to run this across the whole corpus. The function below I can easily use for local testing or other experiments I might do. The fact that I'm going to execute distributedly on Spark is sort of like a minor detail in this actual method. It's very much focused on doing one thing right, and then using something like Spark for a nice horizontal scaling strategy. So when we moved to Spark, we had a lot more confidence and we had a lot more speed moving forward in the build pipeline. We were able to add a lot more NER models and classifiers because it's a lot better to develop on top of this. With the exception of closure serialization issues, Spark is just distributed Scala collections. There's nothing that's special about it. You really don't think about the fact that you're running on Spark a lot of the time. It's very straightforward. Crank out some Scala code and then run it on a cluster. All right, and so to be a little provocative, I really think that machine learning is software. Data science and engineering can move and operate at different timescales, but ultimately, data science hopes to create software that is shipped in production. So I think a lot of the lessons we know from software we can apply to data science and build pipelines. Very much so, don't overthink things, don't prematurely optimize. Profile these things while they're running to get a sense of what are the things you can attack to make them faster if needed. So the new version of the build system I like to call the sentence pipeline. So we're still on Spark, but instead of dealing directly with Mongo during the build process, we use Parquet as an archival format between steps. So yeah, I think this project was a very good problem to have for our company. We've added a lot of systems and to the build pipeline, but it had become more complex and very cumbersome to run. So over time, as we added more and more NER and classifiers, it's not just these individual systems, but the interplay between them that is very valuable. So nice problem to have, but we needed to do something to decrease the time it was taking to do builds. So this is at first this was not very painful, but every step in the old build process would go read from mongoDB and then write in some sort of update to mongoDB over time. There are a number of issues that happen with this. So one is that it's very hard to reproduce states. Unless between every build step you do a Bison dump, you have no real way to say what was the actual input of this job without restarting the entire process. The other thing is that the original storage engine from Mongo did horrible with text. Wired Tiger brought compression to the mix and really helps things out. But under Wired Tiger, if you update the documents after insertion, then you end up basically doubling the database size. They don't really do a good job of providing a vacuum-like facility for databases that you are updating. And the corpus isn't huge. We were easily doing pretty fine with a single node Mongo setup. We could have scaled that out. That would have come with a lot of overhead. But with Parquet, you have I/O that scales on the read and write side with the cluster size naturally, and you don't have to think about the database administration side of that. Yeah, and just to diagram this out, instead of having this one sort of cluster of hard to reproduce state, we have any of our Parquet archives we can use for an experiment for the next build. So if we want to do 10 variants of one step, we can easily do that and have a really nice operational story for how we'll get there. So the results of this work, we're able to take the build time down from 10 days to 2 days, stay on pretty modest cluster sizes. We are able to run a lot more experiments on top of the NER that we have in our system. And we have a much better development story. So before, it was very hard to say what the state of Mongo was at each step. Now with these Parquet archives, we can just pull whatever subset of the corpus we want down locally, do local development, Spark Notebook, and then we're ready to do deployment on a cluster on Amazon. So a little short on time. We are hiring in this for our 2 spots that are related to machine learning and data engineering. So if you're interested in this stuff, please get in touch. Then, like I said, I am running short on time, but I have a little Spark notebook here showing off a little bit of our code. So really like working with Spark notebook. If you're Spark shell and the REPL can be nice, but like being able to easily shift between graphs and code works out really nicely. Add our assembly jar, start a SQL context and load some Parquet up. Here I've got all of our opinions from this particular subset with topics, and then I filtered down to the sentences that have key terms in them. So from here, if I had a little more time for today, I would say we could look at, try and look at some covariance between topic spaces and the key phrases. But the nice thing about this work is we can easily look at our corpus and also see what the machine learning system has said about each part of that corpus. Yeah, any questions?
What library do you use for NER?
So we are for the most part a Stanford NER.
So what I heard, you might have a colonized store.
Yes.
And in terms of searching, if I search by the field that you store in mongoDB, it's okay. How about suppose you have a huge text area, and even though you come from the citation set, you can avoid to define relevance graph. But some of the relevant case may come earlier we ignored. So how can you discover those kind of missing relevance?
Okay, so how can I find the missing?
Maybe I just describe want to as a junior attorney, and maybe naive in terms of the case I was involved. And maybe describe my case in a more naive way.
Yeah, sure. Okay, yes. So in our search ranking algorithm, like we do some pretty vanilla stuff in Solr, but then we also do a re-ranking using the citation network. So if you're an attorney searching, our results are very naturally weighted to highly cited case law, which for the most part is the most precedential and influential.
You mentioned using case library. I was just curious why you didn't use GraphX in that as well.
Okay. So there are. Thank you. So why I use Cassavary versus GraphX? So there are some stuff that we do batch side with GraphX. With Cassavary, we actually do have the database in our app servers for like real-time analytics for the user. So no. There are some algorithms that we actually do want to explore and use in the GraphX package, but just Cassavary really hits a runtime need that we do have. Oh, sure.
You mentioned the use of LDA for computation. Are you doing anything
Okay, yeah. So for the document level topics, we have looked at the terms and given sort of areas of law labels for them. But yeah, it's very much like a human in the loop type process. And the others for LDA is for the summarization. So we have models that are more for the sentence level. And then using those vectors, we do text rank to try and figure out what is the most highly relevant sentences from the opinion.
Jeremy, thank you very much.
All right. Thanks.